Well, hello everybody. Right, we're having a very, very fraught day at the moment. We can't seem to be able to download any of our uh, uh, our PowerPoints today. We're just wondering. We've had some maladies. I was a bit late coming on, so Andy's logged on with everyone on with his phone, and we seem to be having, like I said, issues loading down, getting our presentations up and ready. Roger's got his, and what we will have to do is we will see how we go. We may have to sort of like go along and do each one at a time if we can just load one at a time. It may be because we're actually logged on with Andy's phone. We're not sure.
No,
So,
it's because Mercury is retrograde.
of course.
Yeah.
Oh,
Sorry,
why
guys.
didn't I think of that? Right, okay, and write to your MP and tell people how we're disgusted we are that Mercury's in retrograde. Anyway, thank you very much. Anyway, welcome everybody. We're going to try and muddle on as much as we can. And what we will do is, but firstly, I'd like to welcome all the panel. Well, I have Keith. How are you, Keith?
I'm all right, thanks. Sorry, I'm staring at the wrong screen at the moment, trying to fix this PowerPoint problem. But,
Yeah, I understand. Mine won't load either.
Yeah, sorry about that. If I look a bit vacant, I'm not actually looking at you.
Well, condition normal. Anyway,
Yeah.
what? Only joking.
This picture in the background behind me is not one of mine, I must say, but it's Kemble's Cascade, which is a bunch of stars that just happen by coincidence to be lined up, and you can see they go right behind me, and they're in the constellation of Camelopardis, which is a bit of a mouthful, and I thought people would like to see that, so I put it up. And
just as a matter of interest, you say Camelopardis.
Yeah.
What is that?
Camelopardis.
Giraffe.
A giraffe. Oh, it's a giraffe.
Yeah.
Oh, it's a giraffe. It's a draft. Okay, thanks for that. I'll tell you what, thanks for Keith. You've actually solved one of the problems I've often wondered about. So, well, I've learned something. It's a giraffe. So I'm not going to try and pronounce it again. But anyway, Michael, how are you?
Fine,
sorry.
Yeah, apart from a sore throat and a cough, I'm all right.
Yeah, well, we all saw you were singing and dancing away on Saturday night at your invitation, Beer Keller. But I take it a great time was had by all.
Yeah.
Yeah. And the thing is, of course, you're not an observational astronomer, are you?
No, I'm not.
No, because it was a clear night then, so I can't even chastise you.
I walked home under a clear night.
Yeah, exactly. So I can't chastise you because you've always said you're not an observational astronomer.
Yeah.
So okay, we'll let you off on that one.
I'm a rocket man, really.
A rocket man, yeah.
Yeah.
Okay, then. Well, shape not. There you go. Okay then. Roger, how are you?
I'm okay. Surviving the cloudy weather.
Yeah, it has been. We had a couple of sort of like clearish nights, but they weren't anything to write home about. You just literally get bits between the clouds and things like that. That's all I've had here anyway. But when it has been clear, it's been very, very clear. So, but it just wasn't worth the hassle of trying to get anything out. Even the Sea Star, even though it takes 5 minutes to set up, even probably not even that. By the time you'd done that, you'd have some haze come in or something like that. So, well, I know you've been busy, Rog, because you've been posting away with your moons and things like that. So,
well, that only needs 5 minutes of clear sky, so that's all I can manage.
And unfortunately, the sun has become very boring at the moment, isn't it?
It's almost bald.
It's almost bald. It's completely blank. Everything is just turned off.
There is just something coming around on the eastern limb.
Something's just coming around.
It's not really anything, just a few bits of faculae at the moment, if you pardon my French.
Yeah. So, hopefully we'll get some more of the stuff returning. very soon. But of course, it doesn't really do our sunspot count any good. So we'll be
There's not even
probably
no prominences at all, really.
No, I haven't been looking at the coronagraphs to see whether or not there's anything actually going on the far side. Because if any eruptions happen on the far side, we can still see the stuff being thrown out into space, and that would give us an indication of what's going on. But maybe we'll talk about that a little bit later on. Lou, how are you?
Life is good. Oh, by the way, Roger, where there are faculae, there are sunspots. You can count on it.
Yes, but they're not visible just yet.
Oh, okay.
Yeah.
Anticipation. I'm just packing up my car. I was going to say putting things in the trunk, but for your audience, I have to say putting things in the boot.
That's right.
Yes, correct.
For the solar eclipse, I'll leave early tomorrow morning to drive about 12 hours to Carbondale, Illinois. I'll be there with my NASA peeps, and we'll be live streaming.
Oh, excellent! That's fantastic. Yeah, we're looking forward to it. Even though we're not, like I said, what you showed us last week, we could possibly catch a partial eclipse, but just as the sun's literally coming over the horizon. But I don't know if the sun, if it's clear, then maybe some people might be able to catch something. It'd be interesting to see.
That's enough. Just check the box off. That's all you have to do. I saw it. Check the box. Move on.
Check the box. What was I going to say? You say it's 12 hours. How far is that in miles, Lou?
It's a good question. Let's see if I drive 100 miles an hour.
So that's easy. That's 1,200 miles.
Time dilation, though. I have to
time dilation. Yeah.
No, speed limit 55 now.
Well, it depends. Depends on the interstate. Sometimes some 55, some are 60, some are 70.
Oh, are they? Okay.
Yeah.
Almost
like the Autobahn.
Yeah, I've only driven on 55 roads in the States, so don't know.
Oh, okay then. Well then, okay then.
That's the national speed limit, but obviously not.
Okay then, right then. I'd just like to welcome everybody who's in chat. We've got Ian. Oh, Ian's here for usually a bit late on the Tuesdays. Heidi, hi Heidi.
Hi Heidi.
Who else we got? Oh, Michael Bryce. Yeah, we know who he is.
Ian,
he's
a
troublemaker.
Jerry,
got, Gerard.
Ian and Sandra.
Yeah, I'm just looking for Sandra. Hi to everyone. Anyway, it's nice to see you. As I said, I apologise again that we're having a nightmare of a day as regards what's going on. But what we'll do is we'll first pop straight over to Roger, and he's going to do the night in the sky. Have we got much in the way of a gallery this week?
Well, there's my gallery, and then there's the members gallery.
So we're going to be here all night. We're going to be here all night.
It could be if you're really, really stuck.
This is so embarrassing.
Roger's gallery and some others. Right, okay, then. So but we might as well crack on with it then, Roger. What's going on in the sky this week, please?
Okay, here we go. If you'd like to pop my thing up, if you...
Yeah, there you go.
If you...
Oh, we will go.
Thank you. Okay, so this is the first full week of April, leading up to the event of next week, which we will all be looking forward to in one way or another. So at the moment, we've just come up to the last quarter. And then obviously for the solar eclipse, we will be having the new moon on the Monday. This is the last time I caught the moon, which was on the early morning, few mornings ago, which didn't look too bad at 5 o'clock in the morning. Yeah. So we've still got Jupiter and Uranus now rapidly diminishing into the northwest horizon with Orion and Gemini following soon after. Dominating the southern skies, we've got Leo and Virgo, which we all know contains hundreds and hundreds of galaxies and other interesting celestial objects. and we've got not much else at the moment. But obviously, as the week progresses, we then start to get some of the summer triangle coming up. But I've taken the atmospheric correction off the stellarium here, just to give you a lineup of the planets as they come up in the morning sky. And as you can see, Mars and Saturn are getting to quite an interesting conjunction. And if I go back to the 6th, with the Sun, we've got a very thin crescent, Mars and Saturn on blue. But I would suggest it would be very difficult because of the brightness of the dawn sky, which will probably not help if you've not got a very good, clear easterly horizon. But an opportunity is there if you were able to take it. So, as we progress, we go on to the big event. This just gives you a rough idea of how the progression of the eclipse is going through from Mexico right up through Canada, with the various times of those locations on the map.
If you blow that up a little, you'll see me standing right about there. And
yeah, okay.
Mm.
Now I've got this is where all 7 planets and a comet are in position when the eclipse is at totality. So you may possibly see Venus and maybe Jupiter possibly, but Mercury and even Comet Pons Brooks are all up there at the moment to be seen. But whether there is an opportunity to see them or not is just pure luck, I would have thought.
I mean, that would be one hell of a wide
it would be
skyscape, wouldn't it? Yeah.
That's the photo opportunity of all the planets that are visible, excluding Pluto, which is only a minor
planet. Also with a comet as well. So
Pons Brooks, yes, which is northeast of Jupiter.
Well, that would be really interesting if somebody could catch a wide.
Obviously, with Neptune and Uranus, probably wouldn't be at all because the brightness. But
you wouldn't be able to
maybe Saturn. Maybe Saturn, Venus, and Jupiter, but they're all up there.
We'll be keeping an eye out for that. Yeah, I'll bet somebody will get at least 1 or 2 of those. I should think that would be interesting. Possibly. Yeah. Okay.
Right. Now, just to give you an idea of how much there is available from that, it's all happening just as we get to sunset over here. So looking at stellarium, you've only got the western regions of Ireland that will catch any of it before it sets. So anything further than where it says 20% and partial eclipse, that all happens after sunset.
Oh, of course, I said sunrise, didn't I? Yeah, it's sunset.
No, it's sunset. Yeah. So only the very western edges of Ireland will catch any of it just before sunset. Anything further over onto the east coast of Ireland or Scotland, Wales and Cornwall will not see anything. It only starts to nibble through there when it's about a quarter of an hour after sunset.
Yeah, so, very unlikely.
We'll obviously have to see Lou on the broadcast to be able to see what's going on over there.
Yeah.
But there's still an opportunity to see some of Comet Pons Brooks, which has now gone the other side of Aries. It's still brightening up, but obviously with it being lower and lower in the sky, it does represent a bit of a challenge now, unfortunately.
Yeah, especially with the hour. But also, I mean, I've seen some I've seen some stunning photos, some of your own as well.
Yeah, well, you'll see some in the gallery. So
okay.
Hang on.
Hush my mouth. Hush my mouth.
Spoiler alert. And also through Virgo, we've got Comet 2023 A3's Sunshine Atlas, which will be brightening up through the year and is promising a bit more towards the latter part of this year. So we shall see.
Yeah, that should be an interesting one.
Yeah, it should be. I mean, it's still brightening. It's still not bright at the moment, as you can see, magnitude 11, but it's supposed to go down to about 4.
I should think you'd be able to catch that with the sea star, because, like I said, I caught the Sinskenston, the other one that was about a month ago. That was about 13, 14. So should be able to catch it on the. I'll be on the lookout for that one.
Okay.
Something to watch.
Right. Okay. So here we go.
Rogers Gallery.
No, we have 4 other entries. So please hang on. Right, we've got 2 from Lee. This one is while he was out comet hunting. He's got a wide field shot of Orion, the Hoodies, and the Pleiades. And a very, very nice image it is too.
Yeah, I saw this the other day when Lee posted it on the. I think it was in Facebook. I think it was. But yes, that is a beautiful skyscape. That really is. Nice. Even though you've got the light pollution. You've got, like say, Orion, you've got the Pleiades, you've got the Hyades, and everything. So yeah, that is a really gorgeous photograph.
And there's the signature constellation up on the upper left. That's beautiful.
Yeah, that's fantastic. I think that was actually. I think that was a shooting star that was doing a wiggly thing. So yeah, it's absolutely fantastic how it.
Wiggly stars.
A very wiggly star.
But that is a lovely photograph, and also you can see the foreground as well, which is nice.
Is that the technical?
So here's one of Lee's picture of Comet Pons Brooks, which he also took. And if I put it on, we can see it's roughly in the center of the picture with a meteor. But I notice faintly to the right between the Comet Pons and his signature there's a very slight hint of the Andromeda Galaxy, I think.
I think I did.
No, or something there.
Before,
or is that M33?
Oh, yeah.
Yeah. Yeah, you can see.
There's something there. I think it might be M33.
Yeah,
that's very good. A smudge.
I must
again,
admit,
like I say,
taking night images at Delabole must be pretty risky. There's a colossal hole in the ground there. You might fall into it.
There's a coronal hole in the front of him. Yeah, that is absolutely fantastic. Like I say, these skyscapes are just as impressive as when you get the close-ups.
Absolutely.
And so if you've taken a photograph, even if it's just with your phone, then send it in. There's always something of interest there. It's
absolutely
it's fantastic. I mean, I love these. I mean, this skyscape, and like I say, you've got the comet, you've got the shooting star, and you've also got what seems to be the smudge of a galaxy there. Absolutely fantastic. And again, that squiggly little shooting star in the corner. Yeah,
it's moved across the sky, that one, so it's, well captured.
Yeah, because also you've got some, like I say, you've got some colour in the foreground as well. So it's it's very, very impressive. Well done. Well done.
Keep it up, Lee. Right, we've got one from David Garside, which is of the Whirlpool.
Oh, that's nice.
Oh, that's really
good.
That is lovely.
Very good.
What does he say? What took this image?
He said it's his usual stuff, but can't quite remember what it was. Anyway, it's from Manchester, so I think he's got Bortle 7 skies from that area. So he's done well anyway. Very good. And Jerry, which is also the Whirlpool.
Oh, popular.
Thank goodness I didn't put one in.
Oh, look at that.
Wow. all the dust coming out. All the dust coming out from there.
Yeah, and you can definitely, there's no doubt about the star lane that's passing and the dust lane that's passing between the two. Because, of course, these two galaxies are also, the smaller galaxy is sort of like orbiting the bigger galaxy. And I'm not sure, I've got a funny feeling in a few hundred years' time, you won't be able to see it because it's going to pass behind. So I mean, we won't be here to see it, but yeah, you can see, and also you can see where all the other stars have been thrown out or messed around with the with the clouds of stars that are spilled out into. I do love the Whirlpool Galaxy. I've been able to catch it with a sea star, but not to this detail. That is absolutely fantastic.
Very good.
That is lovely. That is lovely. Well done. Look, and there's also, you can see a lot of new star forming going on in there as well because of the interaction, I presume.
Absolutely.
In the lanes on the bigger galaxy. Can never remember which number is which on these two. So it's the big one and the small one.
Yes.
So yeah, that's lovely. That's fantastic.
Oh, here we go. Some solar images of that big solar group that we had over the last week or so, with a closer view in HA and some prominences right on the edge as well. Yeah,
I mean, it was a shame because these prominences on the right here, they, of course, the prominence, the big prominence at the bottom, and the one that you can't see now, it's actually just literally, I think, a little black hint on the limb there. These were the two that gave us all the fun and games last week. Not like this weekend, but the weekend before. And then as soon as they did that, virtually nothing's happened since then. I've been following the sun. We're getting more solar wind than we are anything else. And I can see what you mean about the plages. You can see just below on the left-hand side, just below the equator, you can see the plage coming round. Or the faculae coming in. So there's definitely something coming in there. Now, I haven't checked the sun this week for coronal holes. Oh, yes, I have. Yes, I did. And I think there's about 3 or 4 small ones, and they're all on the face at the moment. But they are small, but they are giving us quite a bit of solar wind. So but there's nothing for them to blow towards us, no CMEs. And as you can see, as we said earlier, it's almost blank now. Because when was this one taken, Rog?
This is just taken a few days ago. So
so these have gone,
just basically gone.
Yeah, these virtually have all gone now. These spots on the right there. So so we've got virtually a blank blank sun, but we will see what's coming round the corner. We certainly will.
We certainly will. Right. Okay. So here are my contributions to Comet 12P Pons Brooks. I did put one in last week, but there's been another few opportunities, and these are on the 30th and the 31st of March.
God.
And as you can see, there's quite a difference between the tails of two successive nights, where one's sort of blown to the left and the other one's blown to the right.
Yeah, that is strange. So it must have moved some distance to be able to do that. But also the one on the left, you can see the hint of a second tail coming off, can't you? To the the right,
it's a bit more defined. So
so that is strange. And if anything, it looks like the one on the right, you had the better skies. So
yes,
I see you got
better image processing.
Yeah, I think
it's all basically done the same.
Yeah.
Okay.
And you got a pesky satellite in the top left.
Yeah, that came early on. Yeah, I mean they were both taken for about the same duration, but
there is quite a bit of difference in them. Yeah, but they're still lovely. Yeah. If anyone gets a chance,
the star on the right image is Alpha Aries, which is Hamel.
Yeah,
Hamel. Oh, okay. Then.
Yeah.
I mean, the comet's almost the coma is almost as bright as the star, isn't it?
It did seem to be quite bright too. Even on a short exposure. So it's obviously because it's getting nearer and nearer to the sun. It's obviously interacting and generating more coma material. So,
do you know roughly what date it'll be impossible for us to photograph it, Rog, and when it'll drop below the horizon?
Well.
I didn't want to put you on the spot. Say no.
All right then.
No, I didn't want to put you on the spot.
I would say in the next 10 days, which would be almost impossible for us. I would have thought.
Okay, then. But we've got Tintiscan Atlas to look forward to.
Yeah, and that concludes my gallery and others.
Oh, well, fantastic. Well, thank you, everyone.
Thank you.
For let me just get this back.
Get me off. That's better.
Come on and pull you off. So there. Right, okay then. So we'll just get everyone equal. We don't want no favoritism here. Keith was looking grand there. Right, thanks for that, Roger, and thanks everybody for putting in your images. Like we said, anything that you've got, even if it's just taken with your phone or a bog standard well, there's no bog standard picture of the moon. Remember, don't take anything of the sun unless you've got the proper equipment. Always make sure you're covered with filters and everything else. Don't be even think about staring at the sun, even with the naked eye. It's a dangerous thing to do. So please use proper equipment. But anything that you've got, night scopes, anything that you've seen, because also even with I haven't actually tried it. I should do actually. With the cameras today, you could probably take a nightscape, and you could probably yourself pick out the Andromeda galaxy, because it is quite a distinct smudge when you catch it. But of course, you'll probably have to use sort of like the night features on the phone. But if you've got a small tripod and with a phone holder, then use that. Failing that, just put it on a flat surface and use something like a half bag of rice or a half bag of sugar, and you can actually use that. And because it's malleable, you can actually shape it to actually point where you want it to directly do it. Where there's a will, there's a way. But try, if you're going to do it with the night shots, then you have to keep it pretty steady. That's the easiest way to do it. Just use a bag of lentils, beans, or whatever, and then just put it in there. Make sure it's in the right angle. Don't even use your finger. You can always use your voice control, or if you've got a remote control, and take an image. And you'll probably find you'll be amazed what you can catch. You'll probably, if you've got it in the right direction, you'll have the Andromeda galaxy plus the double what do they call them? Star clusters. That's it.
Double clustering.
I'll call them star blobs. The double cluster in Perseus. And you'll be amazed what you can find out. And you may even be lucky enough, if you've got it in the right direction, catch a comet or something like that.
Just to say that I, a few years ago, managed to capture Andromeda Galaxy with a standard DSLR tripod, 3200 ISO, and 30-second exposure. And got the
exactly. I mean, when you do these the phones now, you put them on night mode. You can some of them you can even change the ISOs. You can if you put it in pro mode, and you just play around with it and see what you can get. And it's so simple to when you do a wide angle shot of the night sky, what you can pick out.
And that's the same with the picture behind me as well. That's the same sort of exposure.
Right, thank you. Yeah, so that's brilliant. Hello, Andy.
Andy.
Hello, good evening, viewers.
Good evening.
A bit delayed today. Excuse me. I'm just.
We're all here on time.
Sorry?
We're all here on time.
Oh yeah.
We had some fun and games trying to get our PowerPoints put up, but I think we've succeeded, most of us. So
good.
We succeeded. Now Keith had a lot of trouble, but he succeeded in getting his sorted out.
Oh, good.
I managed to get mine loaded just in case we need it. It's not necessary, right. But yeah, it's nice to see you.
Good to see you too.
Sorry.
Why is Keith so big and looming in the background?
What do you mean in the background?
He's not. Oh, okay.
No? Well, because when we first came on here, because you logged on with your phone, we had the phone. So we had to sort all that out as well. And we were wondering whether
we were on top of each other, so to speak.
Whoa! Not for the first time, I'll wager.
Anyway.
Well, good evening, viewers. How is everybody? Hope you all had a great Easter. Thank you for coming back this evening for Space Oddities. We're back after the Easter break, and I gather Keith is going to present the final part of Astrometry this evening. I hope he hasn't already done so and I've missed it.
No,
not yet.
Okay, great, fantastic. Well, I'll let you carry on. Sorry to interrupt you, but there we are.
All right, okay then. So shall we go to Keith next then?
Sounds like a plan.
Sounds like a plan then. Right then, Keith.
Let's, if I can get this to work then. Yeah.
That's all right. There you are. I can't see it on underneath your thumb now.
No.
No, I can't either. Hang on a minute.
Have you clicked present?
No, and I'm doing it now. There we go.
Yeah, there you go. Right. Okay then.
As always,
you've split it in half, haven't you?
There we are.
I have. Yeah.
Yeah. Okay then. Right. Okay then. Let's just make you big. There you go.
Right. Thanks very much. Right, folks. We're coming to the last part of astrometry, measuring the universe. Those of you who've been here from the start will know we had a few technical issues. So what I've done is I've split the presentation into two smaller parts in order to get it uploaded. So there will be a commercial break in the middle. Right. Okay. So today we're going to have a look at a couple of things. The Tully-Fisher relationship and cosmological redshift. As you can appreciate, what we've been doing with this set of presentations is moving to bigger and bigger distances. Tully-Fisher, which we're about to look at, is a method for measuring the distance of spiral galaxies. Okay, health warning, of course, like all these astronomy presentations, it does have some arithmetic and maths in it, but I promise I'm not trying to make it as digestible as I can. So let's see where we go from here. Right, now the Tully-Fisher relationship for spiral galaxies actually examines the rotation rate of these galaxies. And the rotation rate is determined by the mass of the galaxy, the mass including, of course, all the stars you can see, and the dust and other objects, and, of course, the dark matter, which you can't see, but is definitely there because of the way the galaxy rotates. Now, as you'll appreciate, a galaxy with a greater mass will have more stars in it and therefore will be brighter. And if we can determine the brightness of a galaxy from its mass, which we get from its rotation rate, then we can determine how far away it's likely to be. So that's basically what Tully-Fisher is about. Now, the first thing is you've got to pick the right galaxies to do the work with. This is a set of pictures of galaxies coming up in the Virgo cluster, which is mentioned earlier by Roger. The spiral galaxies, like the ones you see at the top of the picture, they're suitable for the work we want to do. But the elliptical galaxies, which you see on the right-hand side there, are not. So that's what we have to do. And the other thing is we need to pick galaxies that are orientated to us in the most useful way. Now, if we want to measure the rotation rate of a galaxy, in fact, they rotate really, really slowly. For example, our Milky Way galaxy rotates once about every 200 million years. So the galaxy on the right might be spinning slowly round, but you're not going to pick anything up at all looking at it face on as we are. So M101 wouldn't be suitable for our work. On the other hand, NGC 891, which you see on the left-hand side of the picture, because it's side on to us, we can detect that one side is moving away from us and the other side is moving towards us, because any radiation emissions, we're looking at radio waves as much as light, will be Doppler shifted by the rotation of the galaxy. In other words, the waves that reach us will be shortened on the side approaching us and lengthened on the side moving away from us. So basically then, we're going to have a look at one particular galaxy. This is NGC 7331, and it's part of Stephan's quintet. And you can actually see the other four galaxies above it in the picture there. clearly they're much further away. So the quintet is a line of sight thing with 4 galaxies further away and one in the foreground here, which appears to be part of the group, but is in fact a lot closer to us. Now, if you look at the graph on the right there, what one picks up is that the whole galaxy is moving away from us. Well, it would be because the universe is expanding. But one side of it is moving away from us slower than the other side. Why? Because in addition to the velocity of the galaxy away from us due to cosmological expansion, we have also the rotation of the galaxy itself. So we're picking up a side that's moving about 600 kilometers a second away from us, and the other side moving at a bit over 1,000, about 1,040 kilometers per second. And of course, there's a variation, therefore, between the two sides of 440 kilometers per second. But we have a problem here. And the problem is that NGC 331 isn't side on to us. Clearly, it is at an angle, and therefore it looks elliptical. So we have to measure the long and the short axis of the galaxy in order to get a ratio, which is 1:4, and we put that into our formula. Okay, so here we go. Now, the formula, don't worry about where it comes from, but basically that formula at the bottom left-hand side of the slide there is in order to change the velocity that we observe to the true velocity of the galaxy spin if it were side onto us. So we corrected for the orientation of it. And it turns out that, in fact, the difference in rotation between the two sides is not 440, it's more like 454 kilometers per second. So we got that sorted out. And then the thing is that by collecting lots and lots of data from lots of galaxies, we're able to determine that a galaxy that's spinning at about 450 kilometers per second has a magnitude which we get from the vertical axis here of about -20, which is pretty damn bright. By the way, it is very bright, of course, because remember, this is a log scale. But bear in mind also that at -19 magnitude, you've got a single supernova. So supernovas get very close to the total brightness of the galaxies in which they explode, just one star, which is quite extraordinary. Okay, so we've determined for our galaxy here its absolute magnitude, which would be how bright it would look from a distance of 10 parsecs, to be -20. Now, when we actually look at it in the sky, of course, it's a lot fainter than that because it's a long way away. And in fact, the apparent magnitude is +10.4. Okay, so we've got two bits of data there, one derived from Tully Fisher and the other from observation. And we put them into our good old friend, the distance modulus. And when we crunch the numbers on that, out comes the answer of 12 million parsecs. So that's the distance to NGC 7331. And I checked actually and it turns out the official answer is pretty much 12 million parsecs. So the measurements I did on that photograph, and I did it all myself, I didn't borrow it from anywhere, turned up the right answer. But then, of course, it probably would, because I suspect that the official answer was derived in exactly the same way as I did it. Okay, well, the one problem, of course, with all galaxy distance methods is that the uncertainty increases with distance. And you can actually see that here. You can see that these galaxies, which are plotted in terms of distance against the velocity they're moving away from us due to the universal expansion, you can see that the error bars get bigger and bigger on the data points. And also you can see the scatter of data down the bottom left there is getting wider and wider with distance. But nonetheless, it gives us a handle on how far away these galaxies are, because we need that information in order to understand cosmological redshift more effectively. And here we go. Now, cosmological redshift is the stretching of space itself as the universe expands. And any radiation that's passing through space get stretched with it. So waves of electromagnetic radiation, which could be light, ultraviolet, infrared, whatever, radio waves and so on, they get stretched as the universe expands. And the more expansion, the more they get stretched. So the further the waves travel, i.e. from more distant objects, and the older the universe is, the greater the redshift you get. And the one strange thing about it is, in fact, actually, it doesn't matter which way you look out into space, everything appears to be moving away from us as the universe expands. We appear to be in the center. But then if you went and stood on a planet in another galaxy, you would discover that you appear to be in the middle there as well. There is no center. Everybody appears to be in the center without actually being so. And one of the clever ways of depicting the way the universe expands is the balloon model. Basically, if you can imagine a balloon and you put some dots on the outside with a felt tip pen, and then you inflate the balloon, then you've got a sort of representation of what's happening in the universe, because as you blow the balloon up, the dots move further apart. In other words, the galaxies move further apart. And it doesn't matter which dot you look at, all the other ones move away from any single dot that you choose on the surface of the balloon. And the radiation passing between these objects gets stretched as the universe expands, hence the fact you get what we call redshift, that is, the lengthening of the waves of the electromagnetic radiation. Now, the balloon model actually is almost a perfect model of the universe, but it does have one flaw. It has a dimension missing. You see, we've depicted the universe as a two-dimensional surface, the surface of the balloon, as instead of having 3 dimensions. But probably at this point, some people are saying, well, there are just 2 dimensions in this model. You've got a couple of dimensions missing. Well, actually, not quite, because the inside of the balloon represents the past, and the outside into which it is expanding represents the future. So you've got time there as well as a 2-dimensional surface representation. Okay. Now, of course, as we all know, the man who discovered that the universe was expanding in redshift was, of course, Hubble. Actually, no, he didn't. Redshift data and distance data were already being collected by a couple of other astronomers before he got round to it. And also, the idea that the universe was expanding had been proposed by a Belgian abbot by the name of George Lemaitre. And he came up with the expansion rate, the Hubble law, which is now called, that the velocity of an object is equal to the Hubble constant, which we'll come to in a minute, times the distance. So the bigger the distance an object is away, the faster it moves away from us. So Hubble took Slipher's data and Lemaitre's law and grabbed the credit for discovering that the universe was expanding. This came as a bit of a surprise to Albert Einstein, who assumed that the universe was static and indeed introduced a term into his equations called the cosmological constant in an effort to stop the universe expanding, so to speak. In other words, his maths showed that the universe was expanding. He didn't believe that it could be, and therefore he modified his maths to fit his belief, if you like. And then when Hubble came along with this data, of course, Einstein said that the cosmological constant was the biggest mistake of his life, that in fact, actually, the universe really is expanding. And that's that, so to speak. Well, you can see from the graph on the right-hand side that the early data for the expansion of the universe, the velocity versus the distance, you can see that it's a pretty bad scatter. The data's all over the place, and we only vaguely got a trend there through which a trend line has been placed. And that's the problem. The problem really being that although the velocity is easy enough to measure, and we'll show you how in a minute, the distance of these galaxies is the tough bit, working out how far away they really are. And in fact, of course, as you already know from the previous talk, we use Cepheid variables to measure the distance to galaxies as well as Tully-Fisher. And of course, picking up more data from more Cepheids and more Type 1a supernovae as well as Tully-Fisher requires a better telescope. And that's what the Hubble telescope was essentially designed to do. It was designed to give us a better value for the Hubble constant. That's how we got the name, in a sense. By the way, there's a story I picked up from somewhere, and I'm really unable to put my finger on where it came from, that Hubble himself was actually a bit of a character. He was allegedly a serial philanderer, and his wife got her revenge by burying him in an unknown location, so nobody knows where he is. Whether that's true or not, I honestly go and check it. I don't know for certain. By the way, I've just changed the slide to show you a more recent graph showing distances, and you can see that versus redshift, and you can see the data has been firmed up considerably since the early days. But it did give us a problem, and right up until the Hubble telescope's launch, we had values of the Hubble constant, which, by the way, is the gradient of that line, varying by a factor of 10 between the highest and lowest values. So really, nobody really knew what it was. Now, this picture here is quite a famous one, actually, because nearly every astrophysics or astronomy textbook has this picture in it, usually, more often than not, anyway. And what it shows you is a series of pictures of galaxies on the left-hand side there. And by the way, they've used elliptical galaxies here. And on the right-hand side, you can see a spectrum for each of the galaxies, which is the white sort of elongated sort of streak across the middle of each of those pictures. The white lines above and below are essentially calibration marks. Now, if you look at the streak really carefully in each one, you'll see a pair of dark lines. They're caused by the absorption of light by calcium ions in the outer atmospheres of all the stars, or pretty much all the stars, in these galaxies. In other words, those stars are shining out light at us, but there's a little bit of it missing, because the light coming from the middle of the stars gets absorbed by these calcium ions. The electrons in those calcium ions grab the light and they spit it out again, but not in our direction necessarily. So you get these dark lines. And there's a pair of them, as you can see, and they're known as the calcium H and K lines. And if you look at each of those spectra, you can see that the black pair of lines gets further and further and further to the right-hand side of the spectrum. In other words, the whole spectrum is shifting to the right, and the H and K lines reveal that that is happening. In other words, in each case, each galaxy is moving away from us faster and faster because the light is being shifted towards the red end of the spectrum, including those dark lines. Okay, so basically, that's the information. And in fact, actually, in more recent times, and I've mentioned them before, Gettysburg College actually produced a series of astronomy online sort of teaching tools. And one of them actually allowed you to measure the Hubble constant using the redshift of galaxies. And there's a whole set of spectra included in this teaching tool. And you can actually see one here in the diagram on the right. And the two dips that you can see on the left-hand side of the spectrum there, they are the calcium H and K lines. And the one on the right, by the way, is one of the hydrogen absorption lines, because the hydrogen in the sun also in the outer atmosphere of each star is absorbing some of the light coming from the interior. Now, basically, what you had to do with this exercise was to measure the wavelengths of the H and K dips using the bottom axis of the graph there, and you can see the values have been entered on the right-hand side. And these values are measured in angstroms. An angstrom is 10 to the minus 10 of a meter. And if that doesn't mean very much, it's about the size of an atom. And to give you an idea, so it's 4,000 atoms long for the waves that are coming from these stars. In this particular galaxy, we've selected, which is called Coma 1. You'll also notice, by the way, in the diagram, there's an apparent magnitude for the galaxy, which we're going to need as well. Now, if you look back to the right-hand table there, you can see what the wavelengths of the H and K line should be if Coma was standing still. And you can see the measured wavelengths are clearly longer than the rest wavelengths. So Coma is moving away from us. And so you can do some calculations, and the redshift is denoted by the symbol Z, and it's equal to the change in wavelength due to the redshift over the rest wavelength. And you can see we've got two values here for the H and K lines. Each one is pretty much 0.02. I've averaged them out at the bottom there. Now, at this point, folks, is commercial break time, because what I've got to do now is load up the other one. See if I can do that. All right, bear with me.
Why
Would
do
you
you
mind
do
if I made just a quick comment? The Hubble constant is important because of the units that it's measured in.
Yes.
Right, so it's measured in kilometers per second per megaparsec. And if you do your dimensional analysis on this, you find that it's distance per time over distance, and that gives you 1 over time. And that time,
yeah.
Hopefully I'm not preceding your comments, Keith, but that time is the age of the universe in seconds.
It is.
Oh, wow.
Yeah, because also you mentioned Hubble there. Of course, this he discovered that the galaxies were separate items from the Milky Way. And this goes back to the great debate of 1920, which was Harlow Shapley and Herbert Curtis, when they discussed the static state theory, and also sorry, that's the wrong debate. Where they were discussing whether or not what they called star islands were actual galaxies in their own right. And it wasn't until Hubble, I think it was 1926, I may be wrong, correct me if I am, then discovered that the Andromeda galaxy, using Cepheid variables, was in fact outside of our Milky Way galaxy, thus proving star islands were galaxies in their own entity. The whole story around that period of time, and if you look at it, we have got, I think it's one of the basics that we've put up, and it could be in Heroes of Astronomy, where I tell the tale of that era. And there's a lot of very famous names involved in all of that you don't normally hear. As regards, Hubble's always given the glory, and so, but you don't hear about all the people whose work came before them. So I think it's called I think my thing was called Standing on the Shoulder of Giants, and it tells a whole story. So have a look out for that. Sorry, Keith, I just wanted to pop that in there. So.
And just before you
I'm
start,
glad you did, because it gave me time to. I've got the second presentation up below my picture, but I can't start it at the moment.
Right, we'll do that. Just out of interest, Keith, I've just done a quick search about Hubble's grave, and apparently it was his wish that he wished to be buried in an unmarked grave.
That's interesting.
Yeah.
It was alleged to be the revenge of his wife. But...
Yeah. Who wrote the history? But also, of course, Hubble was he was fascinated by English gentlemen, and that's how he behaved, he acted out his life. He spoke in an English accent, and also this is why he's all often seen smoking a pipe.
Yeah.
So he was sort of like, he probably, well, of course, in America, the women were falling over the Englishman. They love the accent.
And they still do.
Yeah, so I've booked my ticket. It's so of course he lived this sort of a bit of a fantasy life, but he was a true astronomer as well. So yeah.
Also, apparently, the location of his grave was known only to his wife and 4 other people, and it's never been revealed where he was buried. Although somebody on the internet is claiming that he's buried in Oxfordshire behind Blenheim Palace. And says, I visited the grave, I have a photo of it, and there's a link to the photo, which sadly is not on the internet anymore because it was 7 years ago. But I'm pretty sure it wasn't that Edwin Hubble.
That'd have been more than one. Yeah.
Okay,
there you go. Yeah.
Anyway, are you ready, Keith?
Yeah, we can go. Yeah.
Okay.
Thanks for the giving me a gap there.
That's all right. Catch your breath and all that. There we are. Off we go.
All right. Okay, so what we got here is the velocity calculation for that galaxy Coma 1. Now, we worked out that the Z value was 0.02 for it, and we just multiply that by the speed of light, and we get the velocity of the galaxy. And it's moving away from us at about 6,000 kilometers a second. On the right-hand side here, you can see some other galaxies and their speeds and their distances. And actually, this data hasn't come from the Gettysburg College software. I just took those straight off that famous photograph I showed you earlier on. And in fact, if you went back and looked at it now, you would see that the numbers were actually written underneath the spectra and underneath the pictures of the galaxies. So we can plot this data. We can plot the velocity and the distance and determine the gradient of the line. In other words, the rate of increase of speed with distance, which is the Hubble constant. So that's what we're going to do. And there it is. So I'll put this into Excel, and you can see for those 5 galaxies you saw in the picture, this is the trend line you get. And so the velocity is on the y-axis, and the distance of these galaxies on the x-axis. And the trend line actually gives you a gradient of about 50 kilometers per second per megaparsec. And that reveals the age of the picture, actually, because it dates back to the late 1940s, if I remember correctly. And that was the determination of the Hubble constant at that time. But since then, we have, of course, pinned that down much more accurately. And the current value is just a little under 68 kilometers per second per megaparsec. By the way, my slides got smaller. I don't know if anybody knows. There we go. Yeah. And as I've already said, the early values were really way out. They were sort of 10 to 100 kilometers per megaparsec. So it was nice to pin it down, which using the Hubble Space Telescope images of Cepheid variables, using Type 1a supernovae, all the rest of that stuff, Tully Fisher, all of those enable us to get galaxy distances more accurately and therefore determine the Hubble constant more accurately. But it's still something that's a bit of a movable feast, as you'll discover if you can watch it from year to year. New estimates come in, and it has varied, because initially it was thought to be around about 70 when the new data came in. It's actually gone down very, very slightly. Anyway, there we are. That's approximately what we think it is today. Notice I use the word today. That's important. I'll come to that. Okay, so as I've already explained, it's a case of better calibration. For example, the top picture there shows you a galaxy with Cepheids marked with green circles and a supernova marked with a red circle towards the center. And basically, as I say, space telescopes have improved things enormously. And of course, also, the Hubble constant has been backed up by the cosmic microwave background radiation readings, which, if I've got time, I'll talk about those. Now, Lou said, Hubble constant tells you how old the universe is. It's often referred to as Hubble time. Basically, the age of the universe is the inverse of the Hubble constant. Because basically, if you think about it, if the universe, if you run the film backwards, so to speak, there'll come a point where the universe reduces to the size of a dot. And if the Hubble constant is big, then it means the universe is expanding rapidly. And if the Hubble constant is small, it means the universe is expanding slowly because it took longer to get to the size it is. Now, one of the problems with the value that I gave you earlier on in kilometers per second per megaparsec is, of course, there's a horrible mixture of units there, and we need to kind of resolve that. But before I do, what does it actually mean? What it means is a galaxy 1 megaparsec away from us should be moving away from us about 67.8 kilometers a second. And if it's 2 megaparsecs away, then it's double that value, about 130 or so, or whatever, 140. So that's basically what that means. But we need to convert it into compatible units. So we've changed the kilometers per second to meters per second. We've changed the distance megaparsecs into meters. And the value for the Hubble constant is actually a little over 2 times 10 to the minus 18, a very tiny number. And the units are not seconds, but per seconds. So we put the value into our formula, 1 over h, the inverse of that value, and we come up with a time of about 4.5 times 10 to the 17 seconds. And if we convert that back to years, we get an answer using this data of 14.7 billion years. Now, you'll realize actually the universe is slightly younger than that. It's about 13.8. So is there something wrong? Well, there's something that we've got to take into account, and that is that the Hubble constant may not be a constant. That in fact the rate of the expansion of the universe changes with time. And that was what Sol Perlmutter and his team discovered in the late 1990s, and indeed received a Nobel Prize for doing so. That discovering that distant Type 1a supernovae were about 10 to 15% dimmer than expected, they realized that the universe's rate of expansion was not uniform. Okay, well, therefore we've got this sort of traditional picture of the universe expanding in a steady line, like the blue dots on the graph then. And then we've got this more modern interpretation of the universe starting off expanding slowly and getting faster with time, which of course does beg the question is what the hell's causing it? Well, if you've opened a cosmology book in the pre-1990s era, you would have seen diagrams very much like the three on the left that you see here. One model had a universe that expands, gets to a certain size, and then because of mutual gravitational attraction between everything in it, starts to collapse again and ends up in something which they referred to at the time as the Big Crunch. And then there is the critical universe, as it's called, which expands from the Big Bang, but the rate of expansion is slowing with time until eventually the expansion stops at time infinity, if we ever get there, which we won't because it's infinity. And then we got the coasting universe, this steadily expanding universe, and all of those were proposed as possible models. But the actual model of the universe we got is the one on the right. It's not only expanding, it's expanding faster and faster. Something's got to be causing that. And the first thing we need to bear in mind is that what's holding it together? Well, the answer is gravity. And the critical mass you need in the universe to stop it from, to get a critical universe, that's the second model from the left-hand side, the density of the universe has to be given by that formula there, where h is the Hubble constant and g is the universal gravitational constant. And if you actually do that calculation, you find that you need about 8 times 10 to the minus 27 kilograms per cubic meter. So a piece of nearly empty space has to have about 8 hydrogen atoms in it in order to have critical density. But we discover actually that in practice, sorry, did I say 8? I meant 5. 5 atoms per cubic meter. The real value is a lot lower than that. We find that on average, the universe has about 0.2 atoms per cubic meter of space. So it's only got 4% of the amount we need to make it critical. Of course, we're only talking here about baryonic matter, the stuff we can see. We haven't included dark matter in our calculations. Well, basically then, we've got a universe that hasn't got enough mass in it to create enough gravity to stop it expanding. But in addition to that, we've got this accelerating rate of expansion, which is a bit of a mystery. Now, back in the 1940s, an experiment called the Casimir effect was carried out. They discovered that 2 plates close together in a vacuum were pulled towards each other by something that couldn't really be explained, but it's often referred to as vacuum energy, although probably vacuum force would be a better name for it. And it's thought, and this is only one theory, that what's actually happening is if you've got a piece of empty space with apparently nothing in it, there are particles that are appearing and disappearing very rapidly. Virtual particles that pop out of nothing and disappear into nothing. And it sounds absolutely implausible that such a thing could happen. But if you do this over a very, very short time scale, it falls under the fuzziness of Heisenberg's uncertainty principle and enables this to happen. And we think that this activity is what's causing vacuum energy. And it's basically a characteristic of empty space itself. Now, that's important because if it's a characteristic of space itself, it means the more space you've got, the more vacuum energy you've got. And of course, it's also known by another name, dark energy. But the amount of mass in the universe, or at least let's say observable universe to be precise, doesn't change. So as the universe expands, the existing mass gets more finely and finely dispersed, so the overall density of the universe decreases, and at the same time, the amount of space is increasing, so the vacuum energy just grows and grows, whereas the gravitational pull between things decreases, so the universe accelerates. I think I'm going to skip past this actually because we don't really say an awful lot, but the cosmic microwave background radiation has also given us quite an interesting handle on the universe's evolution. The universe, when it first started out, was essentially opaque. You can't see the beginning of the universe because up to 380,000 years after it started, light couldn't travel through the universe without being intercepted by free electrons that were buzzing around on their own, and protons for that matter. So what we see at 380,000 years is, if you like, that's sort of the edge of that screen of invisibility. And we can see that as the cosmic microwave background radiation. It's ultraviolet radiation released by a hot universe at the time, but stretched out into microwaves by the expansion of the universe. And of course, the very earliest observations were pretty crude, which is what's shown at the top of this picture, then improved by the WMAP observatory, orbital observatory in 2003. By the way, that stands for Wilkinson Microwave Anisotropy Probe. Try saying that after 15 pints of lager. And finally, of course, Planck, which, as you know, improved the picture further in 2013. So this is a picture of this very earliest universe. And what's interesting is the dispersal of in the picture of the cold and the cold and hot areas, and the sizes of the you know, the mottling, if you like. And this is something we call the power spectrum. And that's enabled us to get an idea of the structure of the universe, and has backed up all the other cosmological observations about the rate at which the universe is expanding, and etc., etc. Basically, if you think you understand the power spectrum, I certainly don't really understand it that well. So I thought I'd put this diagram in as an aid. Anyway, there we are. But basically, all of this information put together, and you can see how much skipping over I'm doing here. The power spectrum that we've got, which is now much more accurate thanks to the Planck probe, basically reveals that the proportions of baryonic and dark matter, which would slow universe expansion if it had a chance, along with vacuum energy that would speed it up, is dispersed something like in the pie diagram, the pie chart on the right-hand side. So we have this situation, as I used to say to the pupils and students that I talked about, that we have a universe in which we can only really understand, put our hands on, measure, observe with any certainty 5% of the universe. The other 95%, we know it's there because of what it's doing, but we can't see it yet. And that's an extraordinary thing. And I did say to quite a few of them as they were leaving their final lectures, I said, your job is to find out what that other 95% is.
No pressure.
Maybe in my lifetime, somebody really will. Because, of course, the dark energy argument that I've put up is subject to dispute. Some people say we don't understand the laws of gravity properly, that Einstein's laws don't work the way that they should have worked, although they've been tested to death, and they do seem to work. And so there may be another explanation. But that's what we think the universe consists of, that pie chart there. We, our planet, the sun we're orbiting around, the galaxy, everything you can see in the sky is 5%. Right, we're nearly there. So basically, the chart on the left-hand side there shows you how the data correlates. Cosmic microwave background radiation gives us a plot, which is that orange line. And the supernovae data is the blue ellipse, and where they cross over is where the universe is in terms of the density of dark energy and the density of matter. So omega m on the x-axis is the matter side of it, and omega lambda on the vertical scale there is the dark energy side of it. And you can see, actually, if you subtend a line from the intercept over to the left-hand side there, you can see it's round about 0.7, in other words, about 70%, which is what we said, and for dark energy. And obviously the other 30% is dark matter and baryonic matter, which is the plot down on the x-axis. So basically, if we got various models of the universe, which are those lines you can see on the right-hand side there, we've got, for example, if we had a lot of matter, we get a universe that expands and collapses again. If we got lesser amounts of matter, you can see we get those various lines that you see there. But the universe we actually live in is the one represented by this dotted line, in which dark energy is a significant component and matter rather less so. All the other models you see there have no dark energy in at all, because no one even thought it was there until relatively recently. Right, well, that leaves us then with this diagram, which you must have seen on the internet many times. And you can see what it shows you is the universe starting at the beginning, then a rapid expansion phase called inflation. And then when the universe becomes transparent is where we see the pattern of microwave background radiation. And then after that, we got a period called the Dark Ages, in which no stars are forming. And then, of course, we get the universe evolving up to its situation in the present day. And if you look at the trumpet sort of shape of it, you can appreciate that the universe depicted here as a set of expanding disks, you can see that the gradient of the expansion is getting bigger and bigger due to dark energy. Make no mistake, dark energy is a very weak thing indeed, but the bigger the universe is, the more of it you've got, and therefore the more effective it becomes. And so that, folks, is what the universe is like.
Great.
Well done. Yeah, thanks for that, Keith.
Thank you very much, Keith. I think we'd all like to say a big thank you to Keith for his wonderful presentations over the past several weeks about astrometry. Fascinating subject. And thank you for presenting it so well, Keith. And that was absolutely wonderful. So there we are, viewers. That's the story of how we map and measure the universe.
Yeah.
And,
just like to say, Andy, in that last slide, if you notice the where you show the funnel, that it actually runs fairly evenly, and then there's just sort of like a phase change, and it actually starts to expand where it gets faster. Something else that's a bit of a mystery as well. So something happened then.
And I think the other mystery is that as the universe expands, the density of dark matter is remaining the same, which is certainly very weird. But I don't think anybody would claim to have even a basic understanding of dark energy at the moment. We're still in the dark as it is. Yeah, very much.
Absolutely.
But Keith, does this mean that as the expansion is accelerating, then the Hubble constant must be changing, surely?
Right.
Yeah.
Yeah.
But over such long timescales that we're not likely to be able to measure that change.
No. And in fact, that was the flaw, you see. When I did the calculation of the Hubble time, it came out too big, didn't it?
Yeah.
And that was because the value of the Hubble constant isn't constant. If you've got to sort of allow for that, you've got to integrate. Yeah. Anyway,
there was an issue for a while, not that long ago, where we were getting different values for the Hubble constant based on measurements of different types of Type 1a supernova.
Yeah.
I think this has been resolved, but are you familiar with this?
Yeah,
a little bit.
Sorry.
Yeah. Yeah.
Okay. So perhaps they can explain that now, which tightens up the curve. But I think for a while we were getting different values for H naught, whether we measured it with using Type 1a supernovas as standard candles versus the cosmic microwave background, and that was very troublesome. I think this has been worked out.
Indeed. I've also seen a few Sorry.
Yeah. So reconciling the different measurements is a bit of a game. I went to a lecture back in about 2003, I think it was, in which a fellow stood in front of us. He said, all those people who come up with all the crazy ideas about how the universe works, they said they're about to be found out, he said, because we're entering the age of precision cosmology. We do things more accurately now. And indeed, this is the case that with the Type 1a supernovae, Saul Perlmutter's data, I think there's about 20 or 30 supernovae on there, because one of the problems with supernovae, I didn't say this, but it must be obvious to everybody who's watching that they go off unpredictably. You don't know where they're going to be. So if your telescope's not pointing in the right direction, you don't find them. And Saul Perlmutter managed to gather together a few tens of supernovae, but now, of course, we've got thousands of them, and we're getting a much better handle on what's going on. And one of the strange things that was I heard about 3 years ago was that when they look at them in different directions in the universe, we're getting different values for the expansion of the universe.
Yeah.
In other words, it appears it's not isotropic. It's anisotropic. It's not the same in all directions, which is a bit of a shock, because we'd always assumed that whichever way you looked at it, it looks the same.
Yeah, I've seen a good few articles in the popular media recently about that the expansion rate seems to be different depending on which direction we look in, which is another layer of bizarreness to the whole problem. So just what we needed.
Solve it, but that's the great thing. That's what's the fun of being a scientist.
Oh, no, absolutely.
There's always something new over the horizon.
Yeah.
We'll never have the final answer, but if we did, we'd be out of work anyway.
Yeah.
Well, of course, Keith, you say we're coming into the precision of age of measuring things, but of course that just throws up more questions than they actually answers. So, like you say, it's great fun.
Yeah.
Well, it's mind blowing, really, when you start looking at things. And all
I
that.
know that this chap who said, about precision cosmology, he was taking aim at the Sheldon Coopers of this world. He really was. What he was invented, of course.
Yeah.
String theory.
Yeah. I mean, at least with dark energy, I think everybody in the scientific community is agreed that it's actually happening, that it's actually there.
Yeah.
Whereas with dark energy, with dark matter, of course, it's it's still very much open to question, because some people are saying that we've got modified Newtonian dynamics.
Yeah, I'm just going to bring that up.
Yeah.
Because we can't find it.
Yeah.
How hard we look, all of the candidate particles fall away.
Okay. Yeah. But then again, we've talked about this before, but there's no one theory of Mond that seems to plug all the holes either. So
that's fiddled in the books as far as I'm concerned.
Yeah. Interesting times. Right then. So again, thanks, Keith. You have our deep thanks.
Yeah, thank you, Keith. That's fantastic.
Plugging away with your astrometry. All these. This is the 5th one now. So
you can have a break now.
Keith's other videos on astrometry that he's been doing on this channel, sort of every other week recently, then check the videos out on the channel. They're easy to find. Speaking of the channel, we've been creating a series of videos, and you'll find them in a playlist called Astronomy Basics, and we've been trying to put some videos together to ask basic questions about astronomical objects. What is a star? What is a supernova? What is the sun? Etc., etc. You will find them in a playlist called Astronomy Basics on our channel. And this evening, I'd like to premiere the latest one, which I had nothing better to do over Easter, so I created. And this one is called What is a Black Hole? And I hope you're going to stick with us for this, because it's only 11 minutes long, if you can stick with us for another 11 minutes. And it's going to be the first in a series about black holes. As you can imagine, they're quite a complex topic, so I'm going to do it over a series of a few videos. And the reason we're premiering this tonight, gentle viewers, is that we would love your feedback. So while you're watching this, if you have any questions or if you have any comments during or after the video, your feedback would be much appreciated, because it's only by getting feedback that we can improve things. So without further ado, I'd like to introduce you to the world premiere. Well, it's already available on the channel, but nearly world premiere of What is a Black Hole Part 1. And in the first video about black holes, we examine the questions, two very basic questions. What is a black hole, and what are they made of? What's inside them? So we'll look at the formation of them as well. So let's now go to this. And as I said, any feedback, please, we really would appreciate some feedback, questions as well. So anyway, here we go. Hello, and welcome to another in the Space Oddities Astronomy Basics series entitled What is a Black Hole? In this first part, we're going to ask the questions, how are black holes formed and what's inside them? Black holes have long captured the public's imagination, mainly due to their mystery and popular perception that they are destructive, ravening beasts which destroy anything in their path. Films like The Black Hole and Event Horizon have perpetuated the idea that black holes are incomprehensible engines of destruction, dark destroyers of galaxies, the very embodiment of evil. The word black, of course, immediately invokes an image of something unknowable, dark, brooding. Black holes are creatures of the night, stirring our ancient primeval fears about the absence of light and its indelible association with death. Given these negative associations, it's hardly surprising that there is a whole plethora of myths and misunderstandings associated with black holes. Fed and amplified by popular media, these often drown out the actual science behind black holes. Despite the basic fact there is still much about them we do not understand. As astronomical objects, we do know a surprising amount about black holes. We know how they form, how they behave, and roughly how they work. We see the effect they have upon objects around them. We can measure how their gravity behaves exactly as predicted by Einstein. We have at least a basic idea of what lies inside them. So let us start our investigation by asking a basic question. How do black holes form? Astronomers categorize black holes into two main groups. The first is stellar mass black holes with masses ranging from around 5 solar masses up to 100. The second is supermassive black holes found at the centers of most galaxies, with masses which can be measured in billions of solar masses. There is no agreed minimum mass for supermassive black holes, which relates to what we know, or rather what we don't know, about their formation. The most massive black hole we've yet discovered is in the heart of a quasar and is designated TON 618. It has an estimated mass 66 billion times that of our Sun. Between stellar mass and supermassive black holes, it's believed that there is a population of so-called intermediate mass black holes. They should possess at least 100 solar masses. However, as yet we have no firm observational evidence for these objects, although logic dictates that they must exist. It seems unlikely that, in terms of mass, there are no black holes between 100 solar masses and the millions of solar masses we associate with the lightest supermassive black holes. Stellar mass and supermassive black holes are created in different ways. Let's see how. A stellar mass black hole is formed when a star with at least around 7 times the mass of the Sun ends its life in a cataclysmic supernova explosion. Blowing off its outer layers, the core of the star is crushed by gravity so much that its very atoms are squeezed into a tiny point and cease to exist as matter. The mass of the core is still present in this tiny point, which is known as a singularity. What is left behind after the supernova is an immensely strong gravitational field generated by the mass that the core of the star possessed, which we call a black hole. That mass is now concentrated into a point possessing, according to the maths, infinite density and zero volume. We do not possess the language to describe exactly what happens at the singularity, as all our laws of energy, gravity and time cease to apply there. The whole process from the supernova explosion to the formation of the black hole takes only a few seconds. Afterwards, the black hole is orbited by a spinning disk of debris from the explosion, which is known as the accretion disk. This debris is sucked into the black hole like water disappearing down a plug hole. Supermassive black holes are found at the centers of most galaxies. Their origins are hotly debated. With such vast mass, which can be up to billions of times the mass of our Sun, they cannot have formed in the same way as stellar mass black holes, simply because even the biggest stars have masses measured in only thousands of solar masses. We believe that there are two possibilities as to how they formed. The first possibility is that supermassive black holes are formed by the successive merging of stellar mass black holes. That is to say, two black holes of stellar mass merge, and the resulting black hole then merges with another black hole, which itself may be the product of a merger, which then merges with another black hole, and so on in a sort of hierarchy. After each merger, the resulting black hole has nearly twice the mass of the two that merged, eventually reaching what we would call supermassive. Here you can see how it would work. Stellar mass black holes merge to form intermediate mass black holes, which then in turn merge to form a supermassive black hole. It's worth pointing out that each merger may involve more than two black holes. There may be triple or even quadruple black hole systems which merge. We just don't know at the moment. While this idea for the formation of supermassive black holes sounds promising, it has a few problems. The James Webb Space Telescope, or JWST, has observed supermassive black holes in the infant universe existing in early galaxies just a few 100 million years after the Big Bang. These are all infant galaxies as seen by the JWST just several 100 million years after the Big Bang. Each is thought to contain a supermassive black hole, which are too young to have formed from a succession of mergers because there simply wasn't enough time. It is believed that black holes can orbit each other for millions of years, very slowly and inexorably, drawing closer together until they merge. You can see that this would take an exceptionally long time to produce even a lightweight supermassive black hole, yet, just 700 million years after the Big Bang, the JWST has found a black hole with 40 million times the mass of the Sun. The figures just don't add up if we postulate that it was formed through mergers of smaller black holes. Perhaps a more likely explanation is that supermassive black holes were formed from the spontaneous collapse of giant clouds of hydrogen in the early universe. These clouds may have merged to possess enough mass for the cloud to exceed a limit known as the Tolman-Oppenheimer-Volkoff or TOV limit, which is the maximum amount of mass an object can possess before it collapses into a black hole. Assuming these clouds of hydrogen were plentiful in the early universe, which they surely were, they could account for supermassive black holes forming so soon, in astronomical terms, after the Big Bang. It may be that both processes had a part to play in the formation of supermassive black holes. It's an area of intense research. One big question astronomers would dearly like to know the answer to concerns the relationship between a supermassive black hole, or SMBH, and the galaxy which surrounds it. Did the SMBH form first and then the galaxy then form around it, or did the galaxy evolve first and its centre then collapse to form an SMBH? At the moment we don't know because it's a sort of chicken and egg situation, but one intriguing fact has emerged during the last decade or so. A supermassive black hole can influence the development of a whole galaxy, controlling the rate at which new stars form because of the influence of intense jets of radiation emitted from the vicinity of the black hole. So there is a deep relationship between the co-evolution of a supermassive black hole and its host galaxy, which we are only just beginning to understand. Now let's turn our attention to the structure of black holes, which are probably the simplest objects in the universe. They consist of a boundary called the event horizon, and at their cores there is something known as the singularity. And that's it in terms of structure. The event horizon is not, however, a physical boundary. It's simply a place, a distance from the centre of the black hole, where any object crossing it can never leave again, because to do so would entail that object travelling faster than light. In a nutshell, it's the point of no return. Nothing beyond the event horizon can ever leave the black hole, including light, and this is why black holes appear black. What happens inside the event horizon can never be observed because no information can escape. This means that if somebody were to fall into a black hole, they could never tell anybody outside the event horizon what they saw. Because of this, we can never know exactly what happens inside a black hole. We have to be guided by theory only, with no way of actually testing our theories. The singularity should also not be thought of as a physical thing. Like the event horizon, it's a place rather than a thing. There, all our laws of physics cease to apply. Everything we currently know about time, space and gravity stops being meaningful. The singularity represents the place where all the mass of the black hole is concentrated into a point of infinite density and zero volume, and we simply have no maths to describe what happens in such a place. Obviously, talk of infinite density packed into zero volume does not sit well with astrophysicists, so we believe that in reality such a place does not exist, even though it does in Einstein's maths. To understand what is there, we need a theory of quantum gravity, which will unite Einstein's relativity with quantum mechanics. But relativity, which deals with massive objects behaving under gravity, and quantum mechanics, the behaviour of particles at the tiniest of subatomic scales, do not talk to each other. They are simply not compatible. A quantum theory of gravity still eludes scientists after many decades, but the quest goes on. We assume such a theory must exist because it's inconceivable that there are two sets of laws which govern the universe, one for large objects and one for subatomic particles. Somewhere, the two must meet, and that is where we will find our quantum theory of gravity. It's like having two house keys of very different design, only one of which will open any single door, but knowing somewhere there is a door that they will both unlock. Until we have that quantum theory of gravity, what happens at the centre of a black hole will remain a mystery. Well, that's about it for now. I do hope you have enjoyed the first part of our introduction to black holes. Do have a look at our other videos in the Astronomy Basics series. You will find them in a playlist of the same name on our channel. If you have liked this video, please consider subscribing to our channel, liking the video, and perhaps leaving a comment with your feedback, which is exceptionally valuable to us and will enable us to improve our content. Don't forget, if it's happening in space, it's happening on Space Oddities. Thanks so much for watching. Well, there you are. There's hello and welcome to another. Let's get rid of that again.
Don't go for two.
Oh, why not?
That was very good, Andy. Very good. Excellent graphics.
Yeah, thank you. You would absolutely be surprised what a paucity of quality graphics relating to black holes there is on the internet. They're actually quite difficult. I think a lot of the time producing that video, I was actually searching for decent graphics. But anybody who's a graphic designer out there who wants to join Space Oddities to do graphic design for us and do some lovely pictures of things like black holes, would welcome you with open arms. But there we are. Well, viewers, I hope you enjoyed that. As I said in the video, you can find more in the Astronomy Basics series on our channel. So if you know anybody who would like to know a bit more about the basics of astronomy, because I'm sure most of our viewers are well beyond that, then pass the word along, spread the word, as it were. Okay, thank you very much. Thank you, Derek, for that. And Gerard, thank you, sir. And Sandra, thank you very much. And thank you. There we are. Let's get these up. Oh, it's going mad. So thank you all for your comments. Good to know. It's appreciated. And glad you've been watching some of the videos, Sandra. So thank you for that. There are quite a few there, as you've probably seen. I will be producing the second part of the video about black holes soon. Not exactly sure when, as soon as I got the time, because as you can imagine, creating these videos is rather time consuming. But we want to do it because we want to keep you informed, because as ever, if it's happening in space, it's happening on Space Oddities. And Michael is hogging the limelight again, so let's just get rid of Michael. There we are.
Yeah, typical. It's not a dating agency.
No. That's the trouble. That's all he's thinking about these days. So there we are.
Did you see his pictures of him at the beer keller in the Stour Bridge? Yeah.
No, I didn't.
Oh yeah, I'll send it to you. You'll be amazed at what he gets up to. They know how to rock down there.
Was it just a sea of white hair?
No, it wasn't actually. There was
really?
some busty ladies with short skirts on and stockings and gentlemen in lederhosen. So,
Michael, you in lederhosen?
I'm still alive.
Okay. Right then, I think we'll start wrapping things up for this evening, unless anybody's got any other points.
Did Lou have a presentation or something, or a comment to make?
Well, it's just one slide or one comment. I don't even have to put the slide up.
There we go.
There we are.
We can. Okay. Just wanted to give everybody an update on Voyager 1. Back in November, the Voyager 1 spacecraft started sending kind of undecipherable ones and zeros back to Earth. And the amazing engineers and scientists at JPL have been working on fixing that, or understanding it and then fixing it ever since. And it was thought that perhaps this was not going to be fixable, that this may be the end of our communications with the Voyager 1 spacecraft. Even though it's still alive, it's not able to send us back anything that is understandable. However, back in March 1st, a set of commands was sent to see if they could kind of nudge the spacecraft, the FDS computer on Voyager, which is responsible for gathering the housekeeping data, gathering the science data, and sending it back to Earth. See if they could kind of nudge it into sending back some information about what might be going on. And indeed, it responded with something very different, which appears to be, and I think this was deciphered by someone at the Deep Space Network, it appears to be a memory dump. And so with this information, they can compare this data, these data streams, with the data streams they were receiving before the problem occurred. And there is now finally some hope that 22.5 light hours away, 15 billion miles away, that they can fix this thing. And that Voyager 1 can continue on being a productive part of the astronomical community. So we will see. Again, it's 22.5 light hours away. So you send and you receive. You send something, you receive the results. That's 2 days worth. So basically, they send a command about once a week and see what it produces. So it takes quite a while. And whereas before, in the heyday of Voyager, during the planetary encounters, they had about 950 full-time employees at JPL working on this. There is now a skeleton crew of 12 working on Voyager, supporting and working on this problem. So we'll keep you informed as events happen, but it looks like there may be a ray of hope for Voyager 1.
Oh, excellent. That's good. But the thing is, at one stage, I thought you were going to say there was an alien messaging embedded in it. So...
I'm not really allowed to talk about that, Daz.
Okay. If you told me...
Don't feed the trolls, please.
Yeah. If you told me, you'd have to kill me.
Nice answer, Luke. Nice answer.
I'll get the men in black knocking on my door.
Yeah.
Absolutely.
And not for alimony this time. So,
yeah.
Right.
But when you think about it, when you think about how, in modern terms, primitive the Voyager computer is, it's amazing that nearly 50 years on, we're still in touch with Voyager 1 and Voyager 2.
Yeah.
It's I think you can point to many examples of fantastic engineering during the space age, but for me, the Voyagers has got to be top 3.
Yeah.
This FDS, this flight data system that where they believe the problem is, consists of two 16-bit word machines with approximately 8,200 16-bit words per machine. So think about that in terms of the kind of memory that or disk space or however in your laptop that sits on your desk.
It works better than my laptop at the moment.
Oh,
Daz, a bit of blue tack and a rubber band works better than your laptop.
Well, an abacus.
Andy, can I just say thank you for the super likes we've had tonight.
Yeah, I was just going to say that.
Yeah, Gerard £5, Gaza £5, and Ian £2.
Absolutely. Thank you very much.
Thank you very much. Very generous of you, lads.
Very generous of you. We do
you.
appreciate it. And it helps us to keep things rolling here. So it all goes to exactly the right place. And there you are. So there we are. So Voyager, possibly back on the road to recovery. Of course, until they've actually deciphered that memory dump. And there's Michael again.
What's he up to?
Yeah, what's he up to?
Where's he got control?
Yeah, he has. That's the weird thing about it.
Michael.
That's the weird thing about it. Yeah,
He's hacked us. He's hacked us.
Yeah. I actually have a solution to that, which is very easy. So,
that's better.
Ow.
More room for me to spread out.
Only kidding, Michael.
Word to the rest of us.
Yeah, I've been wanting to do that for so long.
Yeah, I bet you have.
Yes, so let's if they can decipher the memory dump, and it looks as though I was reading it's they think it's quite possible to decipher the state that the computer was in when whatever occurred, and then compare that with what it should look like. They'll get some clues as as to what the problem is. And then, of course, there's the question of can it be solved? So that's another thing.
And is Voyager 2 working okay, mate?
Voyager 2 is in good shape.
Yeah.
So far.
Yeah.
Absolutely. Yes. And I hope they make the 50 years. That would be, I'll tell you something.
Yeah.
In 2027, which is the 50th anniversary of Voyager, I think it was launched in May, wasn't it, if I remember rightly?
July and August.
July and August, that's right.
Yes.
No, it was Elvis Presley who died in May. Yeah. So,
Similar.
Which,
What do you mean he's on Voyager?
Elvis has left the building.
Left the solar system.
We're going to hear it now. I can see the Texas.
Yeah, but you can bet that as long as Space Oddities is still going in 2027, which we obviously hope it will be, we will definitely have a mammoth celebration in July and August that year to celebrate 50 years. And don't forget, these are humankind's first interstellar spacecraft. And, if humanity was wiped out by whatever tomorrow, the Voyagers would still keep going for potentially millions of years. Who knows? But there we are.
Yeah, you also Pioneers 10 and 11 out there as well.
Yeah, they're Pioneer 10 and 11 as well. Yes, but I don't think we're still in touch with them, are we?
No, they're dead. Yeah,
they're dead. Yeah, I thought they were. Yeah. So quite a thought, that at least, if the Earth disappeared tomorrow, if humanity will have left its mark on the universe in the form of those 4 interstellar spacecraft.
Yeah, and New Horizons is on its way, isn't
it? Somebody had an idea of putting artifacts on board a spacecraft and then launching it into an extremely long elliptical orbit. So it would come back to the Earth, say 4,000 years in the future, as a sort of living kind of museum coming back.
Time capsule.
Yeah.
Yeah. Can it be? Can we send Ed Sheeran?
Hey, the aliens to get the wrong idea about us.
Yeah.
There was some intelligent life.
Yeah, that's right. That's true. All right, then. So thank you for that, Lou. Thank you very much. And thank you to Keith for his wonderful astrometry presentation. But I happen to know, a little bird told me, well, Keith told me actually, that he's got some other stuff in the pipeline that he's going to be presenting. So we look forward to that, Keith. And thank you very much. And I'd like to say thank you to everybody who's been watching tonight. And as we said, thank you to those people who've bought super chats. And, we do appreciate it, as I keep saying. So we will be back same time next week for another edition of Space Oddities. Do have a look at the other videos on the channel if you've got absolutely nothing better to do, because we're accumulating quite a few videos on the channel. And it would be good to get your feedback on those. And we're always willing to take feedback. If you want to contact us at any time about anything that we do, you can write to us at spaceodditieslive@gmail.com, and that's the same address as for the gallery images. And keep those gallery images coming in because we adore them, and we're very grateful for them. So we will see you all next week. Hopefully, have a fantastic week. Look after each other. Be good, and if you can't be good, be average. So I'd like to say good night to Roger, to Lou, to Daz, to Michael, to Keith, and to myself. And we will see you all next week. So take care from everybody at Space Oddities. Thanks for being here, and we'll see you next week.